Okay, so we worked hard. We worked really hard to find this formula. We used the definition of the derivative and ultimately used Pascal's triangle to find a trend in the multiplication of x plus h quantity to the nth power. And we used that computation from Pascal's triangle to then ultimately compute the derivative. And we found out that a lot of the terms in the expression canceled. The h's canceled away, and we got something that was just n times x to the n minus 1. And you say, so what? Man, that was a ton of work for just a little dinky formula. Well, my claim is that little dinky formula and all of that work can make haste of what took days of class previously. Because think about it, when we did the derivative of x squared, the derivative of square root x, the derivative of 1 over x, that took like almost an entire day's worth of class. And my claim is that the 15 minutes or so we spent on this guy, maybe it wasn't even that much, I'm not sure. The long story short is whatever time we spent on this is now going to allow us to compute all of these derivatives lickety-split in like a couple minutes time. So f of x is x squared. Note, the f of x here is in the form x to the n. And any time you have a function of the form x to the n, you can take its derivative, and its derivative is n times x to the n minus 1. In effect, what you do is you bring the power down in front as a multiple, and then you reduce the power by 1. So, bring the power down as a multiple, that's going to be 2 brought down in front times x to the, reduce the power by 1, 1 less than 2 is 1, you have 2x to the 1. But of course, 2x to the 1 can be rewritten as 2x. Ha! That's exactly the derivative that we found way back when. And man, was that not simpler? It was so nice. All you had to do is bring the power in front and reduce the power by 1. 2x, done. Okay, what about the square root function? We computed that using our old school limit laws, and we found that using the definition of the derivative, and we had to multiply by conjugates to get rid of the square roots and simplify, and man, it was a mess. But now, here's the observation. If you think of this not as just the square root function, but as x to the 1/2 power, which is what it is, right? Because the fractional exponent 1/2 is exactly the square root function. Well, then you can take the derivative here using our rule, which anytime you have x to some number, you just bring that number down in front, that's 1/2, and then you multiply by x to that power reduced by 1. And what is 1 less than 1/2? You might have to write this out on the side, but 1/2 minus 1 is 1/2 minus 2 over 2. That's minus 1/2, right? And think about it. If you have 1/2 and you take 1 away, now you're in debt 1/2. So the power here, when you take 1 away, goes from 1/2 to minus 1/2. So the end result is 1/2 x to the minus 1/2. And now, when you look at that, you might say, well, Dr. Bly, that didn't add up. Because previously we got 1 over 2 square root x, and here we got 1 over 2 x to the minus 1/2. But if you then remember that anytime you have x to a negative power, that's like x being divided away, you could then put that power of x in the denominator and say the same thing. A negative exponent is just like a positive exponent in the denominator, and x to the 1/2 is just like square root x, precisely the result that we got previously. Now, it may be in a slightly different form here, but the long story short is this form here is identical to that form there in terms of its value. It may look different on the surface, but it's identically the same algebraically. And the long story short then is this equal to that gives you the derivative of our function square root x, and we didn't have to deal with any square roots upstairs and multiplying through by conjugates or any of that crap. All we had to do was rewrite the expression as x to the 1/2, and then bring the power down in front, there's the 1/2, reduce the power by 1, x to the minus 1/2, done. Okay, what about this guy? H of x equals 1 over x. On the surface, this may not look like x to the n, but if you take a minute to write this as x to the n, and write it as x to the minus 1 power, because 1 power of x in the denominator is precisely x to the minus 1 power. Well, now you can take the derivative. And how do you take the derivative? Bring the power down in front, that's a minus 1, and reduce the power by 1. What's 1 less than minus 1? 1 less than minus 1 is minus 2. So this whole thing, minus 1 times that, is minus x to the minus 2. Problem solved. And again, now you look at that and you're like, whoa, 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 that's not the exact same form that we had previously. But take a moment to digest negative x to the minus 2 and negative 1 over x squared. In fact, when you have x to the minus 2 power, you know that's the same thing as x squared in the denominator. And in fact, then, this is the exact same thing that we did previously. Whereas previously, we took half a class to go through the computation using the limit with fractions inside of fractions. Here, we just rewrite as x to the n, bring the power down in front, and reduce the power by 1. Much quicker.